Today we're going to talk about the fundamental theorem of calculus. Fundamental theorem comes in two parts. One tells us how to evaluate a definite integral, and two tells us that differentiation and integration are essentially inverse transformations. Now we're going to spend 99% of our time using part two, so I'm going to do that first. Before we do that, let's talk about vertical bar notation. If you have a function, f of x, and you have a straight bar with an a and a b, that means evaluate the function at b and then subtract the value of the function at a. So in this example here, 1/2 e to the 2x between 0 and ln 3, this is 1/2, and there's going to be a 1/2 in both the f of b and the f of a. So I like to pull my constants out, e to the 2 ln 3 minus e to the 0. All right, let's just clean this up. That's 1/2. E to the 2 ln 3 is 9, and e to the 0 is 1. Now, the way I got 9, let me do my scrap paper over here. E to the 2 ln 3 is e to the ln of 3 squared. 3 squared is 9, and then we can cancel the e and the ln. Okay, so we get 1/2 of 8, which is 4. Now we can talk about fundamental theorem part 2, which tells us how to evaluate a definite integral. We saw last time we can use areas to evaluate a definite integral, but that's a little exhausting. So the fundamental theorem part 2 tells us that if we find any antiderivative for little f, then the value of the integral will be this number here, big F of b minus big F of a. And if you have trouble remembering that, think Fabio baked many fantastic apples. F of b minus F of a. And I do want to caution you that in my class, this step here is absolutely necessary for me to see. You cannot skip that step. So let's start with an example. We want the integral from negative pi to pi of sine 3x dx. So first of all, I need an antiderivative of sine 3x. Now you can either think, well, what's a function whose derivative is sine 3x? Or you can use your integral Bible. This is a formula right from our integral Bible that I have also included in these lecture notes. So this is negative 1/3 cos 3x. You're not going to put on a plus c. You're going to put straight bar negative pi to pi. So you've already integrated. So you drop the integral sign and you write this. Now we're going to evaluate between negative pi and pi. So the negative 1/3 is a constant. I like to pull constants out. It just makes things much easier. So we've got cosine of 3 pi minus cosine of negative 3 pi, right? And that's cosine of 3 pi. 1 pi is here, 2 pi is here, 3 pi is over here. So cosine of 3 pi is negative 1. And then negative 3 pi also shares a terminal side with 3 pi. So this is minus, again, another negative 1. So what we get is 0. So there's two things I want to point out about that answer. One, the geometry. How can we evaluate an integral and get 0? Well, I've got a picture of sine 3x over here, a graph from negative pi to pi. And remember, the value of the definite integral is the signed area between the function and the x-axis. So we've got 3 loops that go below the x-axis and 3 loops that go above. The above ones count as positive area, the below ones count as negative, so they're canceling each other out. The other thing I want to say is why there's no c in your answer. Suppose you were to add on a c when you found your antiderivative. Then what would happen is the c would be both in the f of b and in the f of a. And so every time the c will cancel with the other c, and you'll get 0 from the constant. So that's why we don't have a c in our definite integrals. You could add it on and you will still get the same answer, but please do not do that. We don't do that in math. It would look really clunky. All right, next one, another integral Bible formula. The 3 up here is a constant. We can pull that out. So this is 3 equals sine, the integral from 0 to 2 of 1 over 4 plus x squared dx. And so again, this is a Bible formula with k equal to 2. So that's 3 times 1/2 tangent inverse of x over 2. Straight bar, 0 and 2. So let's clean this up. This is 3/2. I'm going to factor that out, and then I'm going to evaluate tangent inverse when x is 2, so that'll give me tangent inverse of 1, and then put a 0 in for x to get tangent inverse of 0. All right, so that's 3/2. Tangent inverse of 1 is pi over 4, and tangent inverse of 0 is 0. And so that's 3 pi over 8. Okay, let's do another one. For this one, I'm going to want to rewrite this as two separate fractions, and you then use the power rule. And so I'm going to go through that fairly quickly. Feel free to pause the video and get out your scratch paper if you need to follow along. So this is equal to, I haven't integrated yet, the integral from 1 to 4, x squared over root x is x to the 3/2, plus 2 over root x is 2x to the negative 1/2 dx. Now I can integrate. So this is 2/5 x to the 5/2 plus 4x to the 1/2, straight bar 1 and 4. Again, pause if you need to. Okay, now I'm going to evaluate. This is 2/5 times 4 to the 5/2 is the square root of 4, which is 2 to the 5th, which is 32. And then I add on square root of 4 times 4, which is 8. And then I subtract, and I need to use parentheses because I have to subtract everything when I plug in x equal 1, 2/5 plus 4. So if I clean that up a little, I get 62 over 5 plus 4. Now, your homework will accept that as an answer, but I would want to clean it up and get 82/5. Okay, last one of the fundamental theorem part 2. We've pretty much done this one. This is equal to, when we integrate using the Bible formula, we get 1/2 e to the 2x, straight bar 0 and ln 3. And then this is ... equal to 4 from the very first example on the first page. Okay, let's talk about the fundamental theorem of calculus part 1. Contrast this, which is a number, with this, which is a function. And if little f lies above the x-axis, we can consider this function to be the integral underneath f of t from a to x. And what the fundamental theorem part 1 says is that the derivative of that area function is simply given by little f. And so more formally, this is how it's stated. The derivative of the integral from a to x of f of t dt is f of x. So what happens is essentially this derivative and this integral are canceling, but not in a typical way, because this f of t is being replaced with an f of x. So here's how this works. Let's jump down and do an example. This will be the last example for today. In order to use fundamental theorem part 1 to find the derivative of big F, I need to rewrite it because the x has to be on top. So this is 3 to x, and when I switch the limits, I introduce a minus sign, cos t dt. So big F of x prime is negative, and then I simply take this cosine t and replace the t with an x. There's a lot going on theoretically, but in practice, it's very easy to do. Okay, and that's the end of this section.